Okay, third hour, we're back. I just passed them out. Okay, Pino. Does everyone have a note packet? What, Steve? Steve's right in front of your face. All right. All right. So, from the Pogill, you saw this graph almost exactly. All right. The front page is just the agenda, which, of course, I'm sure will be modified because of all the lovely interruptions in our school day. But nonetheless, this sketch really is to emulate the sketch that you saw in the Pogill about the fact that moles or molarity, if you study a reaction over time, they do not become equal. All right? So if I were to just do a little bit of highlighting and I looked at moles versus reaction time, and I said, let's let the green line represent reactant. Well, you have 100% of your reactant, or however many moles. And once equilibrium is established, that's going to flatline or plateau out. On the bottom graph line, what is that representing? What's it representing, folks? Product. And the product, you see, doesn't exist, and then it starts to form and starts going in the reverse until it plateaus out. Moles are not constant at equilibrium. On the right side, though, I put a little sketch because I do want you to understand about what happens in terms of rate. If I were to graph the rate of the product to the rate of the reactant, rate of the reactant decomposing to the rate of the product forming and equilibrium being established, the two lines would merge like so. And equilibrium is when the rate of the forward and the reverse reaction are equivalent to each other. Sometimes AP will give you a graph like the one you saw here in my note outline already produced and in the Pogill. And sometimes they're going to give you a graph like that which you see up here. So you got to be sure you're reading for understanding and understand the difference. This is rate versus reaction time. This is moles versus reaction time, or molarity versus reaction time. One thing that is important for you to note, and probably the most important thing, rates become constant, moles are not equal. Rates become constant at equilibrium, moles do not become equal necessarily. Obviously, if the mole quantity stoichiometrically was the same, then they would be equal, but that's not an absolute certainty. Okay? So this little asterisk piece here, real important.
Can you move it up? Sorry,
What do you want me to do? Move it up?
The top graph.
Move it down, Kayla?
Oh, yeah.
Okay. So rates become constant. Once equilibrium is established, moles become constant but not equal. Rates do become equal. All right. So a definition of equilibrium before you leave me for lunch. Basically, what is equilibrium? It's a state reached by all reaction mixtures, or most all reaction mixtures, when the rate of the forward and the reverse reaction become equal. And we say it's a dynamic because it's ongoing. Even though no change would be witnessed, it's an ongoing process. Okay? We're going to stop, go to lunch. Okay, third hour, we're back. All right, so equilibrium's ongoing. I've only said that 100 times today. So let's look at a simple problem. All right, fourth hour, you got to be quiet. All right. these problems will get progressionally more difficult, okay? So in this problem, the biggest part of this work is really to recognize what is going on, how you begin, how do you approach it, like most problems. Anyways, this problem says you have an equilibrium reaction of carbon monoxide and water to make CO2 and H2. The reaction contains a mole of each reactant when equilibrium is reached. That's the key, because it's not always going to tell you that. But this one says when equilibrium is reached, the mixture contains 0.430 moles of H2. All right? Question then says, what is the molar composition of the mixture at equilibrium? So the first thing you're going to do is learn how to do what's known as setting up an ice table or an equilibrium table. And so the first thing that you're going to do is you are going to rewrite the equation, and you're going to always promise me you're going to do that. Take the balanced equation, put it in your work, and then off in the margin, what you're going to do is have I for initial. Some people will use C, or I use delta for change, and then E for equilibrium. I believe Ebbing uses C, and that's where this ice thing comes from, ice table. All right. And then what you're going to do is you're going to kind of fill it in and create like a little table here. And because these are only given in moles, we're going to keep them in moles. But if your choice is, and you can have it in molarity, which is usually what you're giving it in, on the AP test and whatnot, you're going to put it in molarity. But I don't have molarity, so I'm going to identify that I have a mole here of each reactant. And at the initial get-go, how much product do we have, folks? What do you assume? You don't have any. You assume you have no product initial. And we will get to the point where we're going to start adding that a little later on, okay? So it's important that you put the 0 there. Now we need to then look at the balanced equation and say, how do the moles of each substance change? We look at the mole coefficients. So this guy changes by minus 1x.
Why minus?
Because reactant will get used up. That's why the negative. I have 1 mole of CO in the balanced equation, so 1 mole of X. So then with that same logic, what would be the change of water? Minus 1x again, minus 1x. Now the product will always be gained, so we're going to put plus. What is the stoichiometry of the coefficient? For every mole of CO, how many moles of CO2 do you make? So it'll be what? Plus 1x. And for every mole of each of these, how many moles of hydrogen do you make? All right. Now if I had a 2 there in the coefficient, 2 water, or 2 hydrogen or something, then I would put that in front of this here. Okay? That's important. And you're going to get lots of practice. All right, and then we add them up. E is at equilibrium. It's the sum of I plus C, or I plus the change, initial plus change, gives us equilibrium. And so we're going to have 1 minus X, and then I'm going to put my unit there, moles. 1 minus X, moles. X and X. And this E stands for at equilibrium. Okay. Now I go and I reread my problem. And I say, what do I know? Do I know X or do I know 1 minus X's value? Read the problem. What did they give us? Did they give us CO at equilibrium, water at equilibrium, CO2 at equilibrium, or hydrogen, folks? Hydrogen. So what we know, after we've set up our ice table, is that this many moles of hydrogen is equivalent to this value at equilibrium, so we know what is X, and that would be the number of moles of hydrogen, and it is also equal to what? Not just hydrogen, but carbon dioxide. And do you have enough information to get what is the value of CO and H2O at equilibrium? Yeah? So I take 1 minus X, which is 0.43 given, and so I get 0.57 moles would be the amount of carbon monoxide and also the water at equilibrium.
We had this before.
Yeah.
You had an introduction to it, yes.
Because I feel like this is one of these questions was on your test once. It asked you for like the ratio.
I don't know. You haven't seen, you might have saw this in last year. And this, you saw it a little bit last year from me. I don't know if Miss Jennings got into it, but I've not covered it this year, unless you maybe have seen it through a review or something where there was some structured group there. Heather.
So if there wasn't 2 for the coefficient of hydrogen, and then would it be 2 plus X?
No, it'd be 2 times X. Great question. So if there was a 2 here, if there was a 2 here in initial, it'd be 2 plus X. But if there was a 2 coefficient here, then the change would be 2X. So 2X would then be equal to 0.43, and then you divide to get what is X. We're going to get there, okay? All right, any questions? So that's a very, very simple problem. So the problems 19 through 43, the first kind you're going to get are very simple. They'll be like this. But as you know, the story goes, we're going to get more layered and more involved in the problem-solving process. All right? So you should have, hopefully, a problem all worked out, like you see here, just like I did. I just organized it a little bit, where you have your ice table, initial change, equilibrium. You have some information about something at equilibrium, and then you can then therefore determine concentrations at equilibrium. You see this hard bracket? That is implying we're at equilibrium. That's going to be an important thing for you to know in this chapter. Okay? Any questions? All right. So let's turn the note page. All right. Well, in this work, you need to become really familiar with what is the structure of an equilibrium constant expression. But before we can do that, you need to know what is an equilibrium constant. Okay, we're back because Pino had to sharpen his pencil. Okay. So, K, the first K you're going to get introduced to is Kc. Kc is the equilibrium constant value. And basically, it's a constant when we're working with moles per liter. And it relates all the equilibrium concentrations of the reactants and the products at a given temperature. It is temperature dependent, and it is unitless, so that's a good thing. Do not put units on your K, it's unitless. So Kc is our first equilibrium constant you're going to learn about. There's all kinds of them. Kp, Kc, Ksp, Kw, Ka, Kb, Kd, Kf. There are a whole bunch, but the reality is, the good news, they all equal the same kind of algebraic expression, so that's the good thing, all right? All their purpose is to relate all the different concentrations of product and reactant at equilibrium. Okay, nothing too difficult. All right, what's the general format of what is K equal? We call it, we set it up algebraically, we call it an equilibrium constant expression. So if this is my generic equation, AA plus BB makes CC plus DD, the Kc value is you take the equilibrium concentration of the product, raise it to the power of the moles, times the equilibrium concentration of the next product, raise it to the power of the moles, and then you divide it by the concentration of the reactant, raised to the power of moles, times the next reactant, raised to the power of moles, and so forth, so on. So the general format, and for pretty much all of the Ks, it takes on this same format. Concentration of the products raised to the power of moles over reactants raised to the power of the moles. Now, here's one sticking point. When you study kinetics, can you use moles to get order? No. But then you're going to spend the next 5 chapters dealing with equilibrium where you're writing these expressions raising to powers of moles. So you have to be very deliberate when you take that AP test that you remind yourself, if I'm dealing with kinetics, I got to remember that I can only make order related to moles if it's an elementary reaction. If I'm dealing with equilibrium, then I'm going to raise to the power of the moles in terms of my equilibrium expression, okay? So I'm pointing this out because this is a common thing that happens to kids, and they get into some trouble when they get these things overlapping. Casey, no, that's Casey's. Hand it to Casey, honey.
Oh.
All right, just have a seat in the back, guys, under the lights. There you go. All right, so let's do a sample problem, very short, sweet, simple. Suppose you got this. And I asked you to write the equilibrium constant expression for nitrogen dioxide reacting with hydrogen to make ammonia and water. All right? This is called a homogeneous equilibrium because you've got all gaseous substances. Just have a seat over there by the door.
All right.
All right, how are we going to do it, guys? Tell me what are you going to get. What's Casey going to be equivalent to? Gordon. All right, so I'm going to take very good. The concentration of the products raised to 2, hydrogen or water raised to the 4th power. That gives me my numerator. And then my denominator is nitrogen dioxide raised to the 2nd power times hydrogen to the 7th power. Now here's one little problem, or one little thing you got to watch out for. In these reactions, only do you keep aqueous substances and gases, not a pure solid nor liquids. They would get eliminated. They are not factored in at all. Okay? And I'm going to give you some notes on that, but I want to make sure you know and have a heads up on that. Yes. You do not count liquids or solids. They do not get put into the equilibrium constant expression. And I'll explain a little bit why that is in a little bit. Okay? Aqueous and gas, you do. Any questions on that, folks? No problems? All right. So with that said, what if we step up the ante a little bit and ask you to solve a problem that looks like this? So this problem says you have a mole of carbon monoxide and water that reach equilibrium at 1,000 Celsius in a 10-liter vessel. The equilibrium mixture contains 0.57 moles of carbon monoxide and water, 0.43 moles of carbon dioxide and hydrogen. Write the balanced equation and then determine or calculate the Kc value. What do you first have to do after you balance this equation that's a little bit different than the previous couple problems? What do you got to do, folks? Well, you got to write an equation. You're going to write the equation in equilibrium. So could you please do that?
Why does it give you all that extra?
Well, that's what we got to figure out. That's what I'm trying to angle at. What information do you need to do something with, and what information can you just disregard? Well, you assume in these that these are all, we'll assume, gaseous. All right? So we write our balanced equation. What's the balanced equation going to be, folks? What's it going to be? CO plus H2O. Have a seat up there. CO plus H2O makes CO2 and H2. And when you balance it, you should get a 1-to-1 relationship. Before you can calculate the Kc, you've got to decide what numbers are you going to use. Do you want moles? Do you want molarity? And do you need to do anything with time or temperature? You do nothing with temp. The reason it's being given to you is because the Kc you're calculating is temp dependent. This value is only at 1,000 Celsius. If you ran this reaction at 750, 900, 950, 1,200, that would not be the same K value. K is temperature dependent. But the thing you want to do is, if you want a Kc, you want to put these in moles per liter before you then set up the concentration of the products at equilibrium over the reactants at equilibrium. So the first step in this would be to, and I didn't do it, that's good, all right, you would get them in molarity. Good news, it's easy math, all right, so you're going to take 0.43 moles of carbon monoxide divided by a 10-liter vessel, so we're going to get 0.043 molar, because
Why'd you do that?
because I want it in molarity, and so I don't want to keep it in moles. I want to put it in molarity if I have a volume to put it in. And then I have to do the same for this one. So 0.57 would be the moles you have at equilibrium. You're in a 10-liter vessel. We're assuming all gaseous. And so I'm going to put 0.043 times 0.043 divided by 0.057. If you want quantity squared is the other way to look at it. Easy. And what kind of answer do we get for our Kc value? You're going to give me 2 sig figs, so we're going to get 0.57, no units. And always when I have no unit things like K, the kid who never uses units tries to put units with K. It just kills me. All right? This one's unitless. Don't put any units. All right? You can make units sometimes out of these things. You don't have units. Now, what does that mean? A K value of 0.57. What does it mean? Does this reaction make product? Does it?
Yes.
Does it make reactant? Does it still have reactant at equilibrium? Does it have more reactant or more product at equilibrium? Well, it's not equal, but they're pretty close, right? But it basically has half the amount of product as it does reactant at equilibrium. Okay? This reaction doesn't go far to the right. It doesn't make a lot of product. That's what that value means. Okay? If it had an enormous K value, enormous being 10, 15, 1,000, 100, then we have a reaction that for all intents and purposes goes left to right, reactant to product, and pretty much doesn't have much of a reverse reaction. This reaction has a significant reverse reaction. And a reaction that barely goes to the right is going to have a really, really, really small K value. And we're going to talk about that in a little bit. Okay, Andrew?
So would a K value of 1 mean it's just perfectly?
Yes. All right, a K value as close to 1 as possible would mean that you have mole-wise an equal number of, molarity-wise, moles of product over moles of reactant, because this is basically a ratio. All right? Parliament.
Always do this in molarity.
You always do it in molarity unless you don't have a choice and you only are given moles, for example. And I think you have a couple like that in your homework tonight. All right? Questions that you have? Gordon.
Does that mean the lower the K value, the slower the rate?
No, and this is not rate. This is how much product exists compared to reactant at equilibrium. It's not about rate. That's a very good question. Did you hear what he said? If you have a really low K, does it mean it's a slow reaction? No. Rate and or equilibrium constants are not the same. This is a ratio of quantity. All right? It's not about how fast you get there or slow you get there. Okay? It means once you get to equilibrium, what can you expect if you could look inside it? What could you expect in terms of the quantity of product to reactant ratio? That's all that K is. All right? Any questions? All right, so let's turn the page and do one more. We're going to integrate both parts. This one I'm going to walk through with you. And this might be the last one we cover today.
Yes.
We'll see.
Yes.
All right. So this problem says a mole of hydrogen sulfide was put in a 10-liter vessel, heated to 1132. It gave an equilibrium mixture containing 0.0285 moles of hydrogen. What's the Kc at this time? So now we're integrating. You got to do an ice table, and then you got to set up a K expression, and then you got to solve for the K. All right? So, for all my people who like to have steps, here you go. Step 1, set up an ice table. All right? So, we have initial, change, equilibrium, and we're going to rewrite our equation above this table so we know what we're dealing with. We're going to do 2H2S, 2H2, and S2. What is the molarity of the hydrogen sulfide initial? Someone tell me. Well, that's 1 mole. We want it in molarity. We don't have a 1-liter vessel, so it's not 1, but 0.1. So we have 0.1 molar. Do you have any hydrogen or sulfur? So you have 0 and 0. Please don't forget to do that, because as the things change, we're going to start adding pieces in there. All right, now here's our new piece. How does hydrogen sulfide reduce? By X or 2X? 2X. So we put minus 2X.
Don't you put 0.1 minus 2?
I will down under equilibrium, Kayla. This is initial and change, and then down here is the addition of the 2. 0.1 minus 2X. All right? How does hydrogen change, folks? Plus 2X. And how does the sulfur change? Plus X. So at equilibrium, these are the algebraic equivalences of each reactant and product. Now, what am I given that I'm going to use to help me to figure out what are these actual numeric values?
0.0285 moles.
The 0.0285 moles of hydrogen, but remember this is moles and we set these up in molarity. So what's the first thing I want to do with regards to this?
Divided by 2.
Alright, so here's how I'm going to do it. I'm going to say, I know that 2x equals 0.0285 moles of hydrogen divided by 10, just so you know where all those numbers came from. Okay, I know this was the equilibrium quantity of hydrogen in moles in a 10-liter vessel. And so I have to divide so that I have it in molarity because all these are in molarity. So therefore, when I do my math, X should be equal to, if I did my math right, 0.001425 molar. Is that correct? Yes? All right. Can you now figure out the amount of sulfur at equilibrium and hydrogen sulfide at equilibrium? All right. So, but one thing, guys, this 2x value is 0.00285 because this equals 2x and 2x is hydrogen's amount at equilibrium. This X value is the moles of S2 that I have. And then for this piece right here, the H2S at equilibrium, and the way I note it is this. I do a bracket, okay? And I should probably do that here. I'm going to take 0.1 minus, that value is this value, I'm sorry, is equal to 2x. So minus 0.00285 molar. And so that value that I get there is equal to 0.09715, Langan, be quiet, molar. You're caught. All right, and what's the last piece? So step 2, I figured out my equilibrium values. That's all this business there. And what's the third step if I want the Kc at this temperature? What do? Put it in a Kc expression. So, what do? Number 3, we say Kc equals, what's the concentration of our hydrogen? That's our concentration of our hydrogen. So we take, you can put it in scientific notation if you like. So we take that, and the hydrogen value has to be squared because it's 2 moles in the equilibrium expression. We multiply that by the equilibrium concentration of the sulfur. The equilibrium concentration of the sulfur, 0.001425. That's raised to the first power because it's 1 mole. Products over the reactant, we have 1 reactant, hydrogen sulfide at equilibrium, which is 0.09715 molar. This has to also be squared. And the Kc value that you get, can someone crunch that for me if you would please? Put in scientific notation, would be easier. I didn't do the work. 1.226 times 10 to the minus 6. Can someone confirm it?
Yes.
All right, so we get 1.226, so 1.23 times 10 to the minus 6, Tim? And that's our Kc value. That's really small. So that means the ratio of product to reactant is really small. So does this reaction really proceed much to the right?
No.
Not much at all. All right? That's what it tells us conceptually. Yeah.
I did the ice table and making ready.
Did you get the same answer? Yeah. Okay? All right. One last one I want to give you, and then I will stop here. Actually, I'm not going to stop. I got a few more to do. You know me. You can handle it. All right, let me do one more. All right. The equilibrium, there's another equilibrium constant. There's many. And this one is called Kp. And Kp is the same mathematical expression. However, we use it when we're dealing with gases. And you do it when you're writing your equilibrium constant in terms of partial pressure. So P stands for pressure rather than concentration. All right? And there is a mathematical relationship between Kp. You can go between one or the other. All right? So let me just give you, I'm going to write how Kp does. Nonetheless, I'll do that here. Kp equals the partial pressure of the products, just like you did reactants, and yes, you raise them to the moles, divided by the partial pressures at equilibrium of the reactants raised to the moles. The only difference here, folks, is you're dealing with partial pressures as opposed to molarities. The relationship between Kp and Kc, another kind of application, is that if you know the Kc, you can determine the Kp by taking Kc times the quantity of RT in parentheses raised to the power of change in moles of gas. And I'll explain that in a second. AP gives you this equation, so you don't, and I will too, you don't need to memorize it. The R value is the gas constant, 0.0821 liter atmospheres over moles Kelvin. Temperature, therefore, would have to be in what unit? Kelvin unit, because we're dealing with gases. And this value here is moles of gas in the product minus moles of gas in the reactant. Product minus reactant. Yes, I will try. I assume you have that, right, Kayla? Better?
Yeah.
All right. So Kp can be, if given partial pressures, the partial pressure of each of the products raised to the power of moles multiplied by each other, divided by the partial pressure of the reactants raised to the power of moles multiplied by each other. However, if we give you, gentlemen, be quiet. If I give you a Kc and a temperature and say, what is the Kp? Then you have to resort to this equation. You take the gas constant R times T, find that product and raise it to the moles of gaseous product total minus the moles of gaseous reactant. Not liquid, not solid. Often this will come up on an AP multiple choice question. And they'll try to get you by thinking, not by trying to make sure you know it's only gas changes that we're looking at, not total moles of product minus reactant. It's only gaseous moles, okay? And I've given you a couple of those in your work to look at this evening, okay? All right. Down here, this would be just kind of a plug and chug kind of problem. But I would like to go through it with you just so that you see how to do it. You can do the math piece. So here's a problem where I have an equation. All of the substances are gaseous. I give you the Kc. I give you a T, but it isn't in Celsius. So I'm immediately going to put it in Kelvin. So I get 464 Kelvin is equal to my T. And I want to get what is the Kp. So nonetheless, I'm going to just do a little bit of plugging and chugging. So I have a Kc. Again, Kp is also unitless. So I have 3.26 times 10 to the minus second multiplied by 0.0821 liter atmospheres over moles Kelvin, which you really don't need the units because of the fact that Kp is unitless. You're going to times that by temperature in Kelvin. And then what is my delta N? My delta N is 2 moles minus 1 mole. So I'd take 2 minus 1. And so then I would get my answer. Okay? So sometimes we want to relate an equilibrium constant in concentration, moles or mole per liter, to that in terms of partial pressure. Are you with me? To the change in the moles of gaseous product minus reactant. So I have 2 moles of gaseous product minus 1 mole of gaseous reactant. All right? If I had solids or liquids, I'd ignore those. Yeah, Dan. Pat.
KP's unitless too, right?
Yes, unitless. Lovely. All right?
Wait, how do you have 2 moles of product?
Because
never mind.
1 and 1 here.
Yeah, I see.
Got it? You got a chlorine and a phosphorus trichloride, and you have a phosphorus pentachloride.
I was looking at it backwards.
All right. One more. All right. One more.
Man, you have to go in 3 minutes.
12:40. Oh. All right.
4 minutes.
Yeah, it's
All right. I'm helping your academic endurance. All right. One more last final concept. How do you find an equilibrium constant when you add up a couple equilibrium equations? So suppose I have a reaction 1 and I have its K value, we'll call it K1, and I have a reaction 2 and I have its K value, we'll call it K2. And I say to you, let's say these are elementary reactions, and I say let's add those up, which then the sum of those would give me a reaction 3, and I'd say to you, what do you think the value of the K would be for the sum of the 2 reactions? Be careful, because it's not adding. Okay? It's multiplying. All right? So when I want to find a K that's come for a reaction that's come by adding 2 reactions up, you have to multiply the K's together. All right? So I'm going to, in here I write, if a chemical equation can be obtained by taking the sum of other equations, the equilibrium constant for the given equation equals the products of the given K values. So therefore, the way I would get this would be by taking K1 times by K2. Again, this makes for a very easy multiple choice AP question if you know it. Our common sense would say add them. You've got to know that when K is derived by adding equations, you've got to multiply.
Wait, and K is just the concept.
K is it's not a K is a reaction, is the equilibrium constant, yes. All right. Too many K words. All right, here's your homework. Yes. Page 642.